saying the same thing, okay? Should we finish it? Or go for a little bit? Okay. So are you interested in IRS or should we conclude it? IRS? So this is only very like introductory slide only, okay? Not much in detail, okay? So IRS you already know, intelligent reflecting surface. So I have 4 sections here. In first, so I took inspiration from Emil Jorson slide also, okay? So we have 4 sections here. One is introduction to IRS, so I'll be presenting some basic stuff. Then I have some IRS modeling. How do we model IRS? How do we use that in this kind of equation, okay? And introduction to beyond diagonal. So this is most recent works, okay? So how we can improve the existing IRS is given in this. So this is still in the theoretical stages. So I will just present what is in the paper, okay? Then some conclusion. So in wireless communication, we have 2 more important resources, transmit power and bandwidth, that we are managing to provide the better throughput. So power, that is transmit power, we are trying to minimize power. We have energy efficient system also. We research on energy efficiency. Bandwidth, we are putting the density closer to closer and also going to the higher bandwidth to get, going to the higher frequency, millimeter wave, terahertz wave to get the more bandwidth, okay? So wireless channels are multipath fading channel, you already know it, okay? And where signal is received by multiple paths. So can wireless channel be controlled? So IRS is one of the way, okay? So IRS means intelligent reflective surface. With IRS, we can control some paths, okay? Okay, so this is one example here. So we have one mobile transmitter and we have base station and we have several buildings, and so there is a blockage also here. So blockage occurs. So blockage shows that there is no direct path here, okay? So when there is no direct path, there will be multipaths, okay? And this signal, let's say, it cannot reach, or it is being transmitted, or it is from this building, it cannot reach here, okay? You can think of like that. But if we put the IRS block here with some IRS controller, and we can control to direct it to the base station. So in theory, or in also in the experiment, we see that even introducing one path helps very much when you do not have direct path. We also see in the simulation also. So if we introduce one more path, that is very, very helpful, okay, when direct path is not available. So IRS stands for intelligent reflective surfaces. There are other names also, reconfigurable intelligent surfaces and software controlled meta surfaces. IRS can provide an extra path and strengthen the existing path between transmitter and receiver, okay? So even if you have existing, let's say here, so there is an existing path already. If you put some IRS here, so there will be less number of less penetration and less transmission will be there, and it will be reflected more smoothly, okay? There will be less losses in this reflection, okay? So when there is a blockage, there is no direct path. IRS can be useful, really helpful, okay? So usefulness of IRS depends on the path loss. So in the path loss, you already know this Friis equation from your undergraduate courses. So PR is the received signal power, PT is the transmit power, lambda is the wavelength, and DTR is the distance between transmitter and receiver, okay? This is the Friis equation. So if you have a omnidirectional antenna, if you have a distance of 10 meter, and we are talking about the 3 gigahertz, so you will have path loss of approximately 62 dB, okay? And If it penetrates the wall, it will cause more than 20 dB of loss. So you will receive very, very minor signal. Okay, so you have to take care. Even if we have some path, it will really helpful at the receiver. Okay, so this is one example here for the office environment or home environment. Okay, we have base station here, we have wall penetration here, we have two users here. So one user is receiving the signal through wall, so it will receive the attenuated signal. Okay, very less. And if we are receiving, we can receive one signal from IRS via some window or via some roof. Okay, so that will be really helpful, and it will strengthen this user signal. Okay, we can receive very good rates. So this is one application in a mall environment. So if we have a mall, we can put the IRS on these surfaces that can improve the indoor coverage. So where there are like many number of peoples are there. So for example, you have like lifts are also there. Its signal doesn't work. Because it goes underground. If you put IRS, it can create multi-path, and there's a possibility that signal will also travel there. Okay. So you can configure this accordingly. Okay. So next section is the IRS elements and their reflection coefficient. So yes, so each element needs to be controlled. Controller will be, you can put central controller or you can put individual controller. So IRS is still in the development phases. So I will show one experimental result also from one of the paper from Emil Johnson also. Okay, so controller you can put, for example, you have this, let's say CCTV cameras. Okay, so you put the wire around and put the controller at some places. So similarly, you can put there. Okay, you can connect it and put the wires around and put some controller at some central server. Okay. Yes, number of elements. Yeah, we will come to the gain. We will come to the gain. How the gain is there. So this is a real world implementation by Emil Johnson group. So what they did, so this is one panel. So in this panel, so I am showing here we have base station, we have mobile transmitter, and we have IRS panel. So this base station is transmitting and it is being reflected, and this is like a pencil beam going towards the directly to the mobile user. So how does it do? So each of its element is consist of a varactor diode. So varactor diode is a works as a capacitor, variable capacitor. Okay, and it is connected to a wireless controller. So it can change the voltage accordingly. So it will. So we have to provide phase shift. So phase shift is kind of a RC phase shift. So you in your undergraduate courses you might have heard of RC phase shift network, right? So that RC phase shift network, we are using they are using the varactor diode, okay, for that, and they are changing the voltage across it so that the capacitance will change. If capacitance will change, the phase shift will change, okay. So that way we can direct the beam accordingly, okay. That is the idea here for implementation, okay. So this is. It is not shown here correctly. This part is not visible. It is visible. So, can you see this part? Okay. Okay, little bit. So what I am trying to say here, okay, I will say directly. So we have this plane wave coming here, and plane wave is going out here. If we have some normal plane like a mirror, okay, and we have some tilted plane, then this wave will come here, this wave will go here directly. Plane wave. Plane wave is the input, plane wave is the output. So this is like a convex surface. So some wave is coming, it will be pointed towards this user, okay. So what we are trying to say here, IRS doesn't act as a mirror, it acts like a convex surface, okay, which can point towards a particular user or particular direction. Okay. So these are the results from this paper. So these are the results for using the varactor diode for elements, so the response for each element. So what does it show? They have varied the voltage between 0 to 19 across the varactor diode element, and they have seen different characteristics here. So the top curve shows the reflection coefficient versus the frequency, and the bottom shows the reflection coefficient phase versus frequency. So amplitude and phase versus frequency. So amplitude variation are smaller in the yellow band. So why they are considering yellow band? Because there is their operating frequency is 5.8 gigahertz. Okay, so they will operate only here and there around the 5.8 gigahertz. So around the 5.8 gigahertz, this yellow band, they see this band, this is approximately equal to 8.8. Okay, and this band, this curve is linear, almost linear. Okay, so they consider only this band, like around 5.8 gigahertz. So reflection coefficients are approximately constant within this band, and thus iris elements have approximately flat frequency response within this yellow band. Okay, almost flat they have assumed. Okay. So what IRS can do, it can direct the incident, some signal that is arriving using the phase shift. It can also absorb the signal. If we can control the impedance, if we increase the impedance too much, that will put the like a resistor. It will obstacle that signal and it will absorb it. And it can also change the polarization by controlling both impedance and phase shift. So for example, these are the different kind of polarization: linear, circular, elliptical. So by changing the polarization, we can also sometimes avoid the interference also. Okay, so let's come to the modeling. Any question up to this point? Okay, so let's come to the modeling. So first we do the signal modeling. So this is very, very basic stuff that you read in the undergraduate courses. So whenever we transmit the signal, we transmit like this. So we have some signal, let's say BPSK or QPSK, whatever we want to transmit. We modulate into a pulse, PT. So let's say square pulse or raised cosine pulse or root raised cosine pulse, and shift it and transmit it. So it will make a pulse, okay, accordingly. So this pulse should satisfy the Nyquist criteria. So this is the Nyquist criteria. That is Pm divided by B. B is the bandwidth. Okay. So that is the baseband bandwidth for m not equal to 0 and non-zero for otherwise. So if we receive signal can be given by like this, the convolution with that signal. Okay. So at the receiver we will do some filtering. So filtering we do with the PT. So it will be given by like this. Okay. There is nothing here. We just do the convolution here. So it will have two convolution here. So after that we do the sampling. So in the sampling, this is the sampling frequency 1 by B. So in the baseband, okay. So sampling theorem says, so this is B, so this is 0 and this is B by 2 and this is minus B by 2. So the maximum frequency content here is B by 2. So by sampling theorem, the sampling frequency must be B at least. So the sampling frequency is B here. So we are sampling here. So this should be 1 here for K equal to M, otherwise it should be 0 for the Nyquist criteria, and this is the effective noise here. So we will get some channel here and the corresponding signal, and for a narrowband channel this HT will be simple flat fading channel, only one coefficient will be there, flat fading. Okay. If you have frequency selected, there will be a multiple taps here. Okay. So next, this shows the similar process. So we have some XF. This is the spectrum, magnitude spectrum, and we do the up conversion to transmit it, and it goes through a channel. So this channel, you should note that it is going in terms of and in this pass band, okay, at frequency FC. So after that, we do the down conversion, and it comes to this. Then we decode this kind of signal, okay. So here we are talking about the end-to-end channel for narrowband channel at frequency FT. So at frequency FT, the channel is like this for a frequency flat channel, okay. Now we talk about the direct channel. After the down conversion, it will have multiplication by this factor, e to the power minus j 2 pi fc into tau d. Tau d is what? Delay, direct delay between transmitter and receiver, okay. Now similarly, we can write the channel between nth element of the IRS and transmitter like this, okay, where this is the attenuation factor, this is the delay to reach from here to here, and this is the phase shift, okay, down conversion from frequency FC to baseband, okay. And similarly, we can write from for the IRS only. Each IRS will have this kind of factor. Similarly, we can write for the channel between receiver to nth element like this. So the effective signal will be like this: yk equals to h effective into xk plus wk. So this equation we obtained in the last slide here. So this h should be h effective when we are including IRS. So this is the direct path, okay, and this is what? This is the path via IRS. So we have n elements, so it will be coming, we will have this factor of n here, this summation n here, and we will have these three will be multiplied, and they are in the exponential, so these will be added, okay. So any question here in this slide? Okay. So let's only focus about the IRS signal here. So in IRS, we have this the same thing here, okay. The same thing I have written here like this. So using Cauchy-Schwarz inequality, everybody know about the Cauchy-Schwarz inequality, right? Okay. So if we write Cauchy-Schwarz inequality for this part and this part, so this is exponential, so its absolute value will be 1. So we can write like this. So what does it show? And this we can approximate like this. So what does it show? If we have n element, it is multiplied by a factor of n, and all the gains will be multiplied. So this is the gain, this is the channel gain from transmitter to IRS, and this is IRS attenuation, whatever it is, like 0.8 we see in the reflection coefficient, and this is the channel gain between receiver to IRS, okay. So with these three will be multiplied, and we have this factor of n here, okay. If we talk about in terms of SINR or power domain, so these will be squared here, so squared, and these gain will be multiplied here, okay. So this equality will be achieved when these three are same. These three are integer multiple of 1 by fc, okay. So these are some experimental result from this paper, okay. So what they have done here, so they have the transmitter here, and they have the receiver here, and they have IRS here, okay. So so this they have zoomed like this here, okay. So this has the distance of 50 meter. So when IRS is not present, okay, so this is omnidirectional antenna. So the received signal is given by like this. So it is around minus 66 dBm, okay. So we receive very little signal, okay. And if we put the IRS here and configure it, it will reflect the signal to here, and we receive nice signal like this. So these have difference of like 25 dB or something, okay. So and 25 dB is very large, okay. 25 dB is very large to detect the signal, okay. We can detect the signal very nicely here compared to here. So this slide show the benefit when direct path is not available. Okay. So when we have one transmitter and one receiver and one IRS. Okay. So this path is minus 75 dB. This path is minus 75 dB, and we have two cases. First case is when direct path is not available. It means there is a blockage. So blockage will cause loss in dB more. So this path is minus 100 dB, and when there is a direct path available, it will be minus 75 dB. Okay. So these two cases, with and without IRS, we have seen here. So case one means when direct path is not available. So we see here, with IRS we have this curve, without IRS we have this curve, case one. So we see this much of difference we have when we increase the number of element. Okay. And when we have case two, when this is 75 dB, we don't see much of difference here. Okay. So what does it show? That when direct path is not available, IRS is really helpful. IRS can be used to increase the spectral efficiency. Okay. And this factor n, so this increases like linearly with factor n. Okay. Any question here? Yes, n is the number of element. Yes. Gain is adding. That's what we have talked about here in this slide. So we have the sum here. So this is approximately equal to factor of n, and n will come here. Okay. So all gain, so between transmitter to IRS, this is IRS attenuation, okay, and this is receiver to IRS, all will be multiplied, and we will have a factor of n here according to this summation. Okay. So we can also compare with relay, how it compares with relay. So relay need a additional time slot. Okay. So if you know about the relay, so first we transmit some signal, relay amplifies this signal, do amplify and forward or decode and forward, okay. Then it forwards the signal. So it needs 2 time slot. So overall, when we talk about the rate, the factor of half comes here, okay. Half mean it takes 2 time slot. So overall rate is half, okay, for 1 time slot, okay, per time slot. So signal can be amplified at relay. This is one advantage of relay, okay. And in IRS, if we talk about it, we have all the 3 gains are multiplied, and we will have factor of n square here that we have seen here, right? Okay. So this will be n square when we go in the SINR domain, and we have relay. Relay gain is like this. Factor of 1/2 is coming here, since it takes 2 time slots, 1 plus this beta SR and beta RD. So this is beta SR, source to relay, and relay to destination. Okay, minimum of it. Okay. So here you see we are getting minimum of it, and here we are getting n square of factor of it. So this is better. So if we have value n is very large, then we can also beat relay. Okay. So this figure show the required transmit power versus the distance to achieve this much. It's written here, R bar equals to 6 bits per hertz. So this blue line is for DF relaying, decode and forward, and this is for CISO system. So when we have different values of n, so let's say for n equals to 150, last one. So we can see this is going after this, after a certain distance. So when we have low distance, this transmit power required is very less. Okay. So when distance is going larger, transmit power required is more. Okay. So here, how do we see this? So when we have increased number of antenna, it requires less transmit power. Okay. Because we have IRS gain to cover for it. So when n will increase, it will require less transmit power to achieve the same rates, 6 bits per hertz, okay, 6 bps per hertz, okay. So this we have already talked about. IRS act like a convex lens rather than a mirror. So in this paper, this comparison is given. So mirror gain is like this. So this plot gives the total channel gain versus the number of element for mirror when we use IRS as a mirror, and when we use IRS as an optimal value of phase shift. Okay, so this is like this, and after in the far field, so only point where an optimized IRS operates an anomalous mirror. So up to this point, mirror is better. So after this point, so when we have more number of element, we can go for the IRS optimization. Okay, so when we have less number of IRS element, it is better to act as a mirror. Okay, that's what it is saying. So we can just assign. So for example, this point comes at around 120 or something. Okay, this is 100 or 200 or something. Less than 200 it is coming. So it is saying. So around those points, if you have a number of points less than that, you can define your element such that it can reflect directly like a mirror. Okay. So this is what we have discussed for conventional IRS. What IRS is made of, presented modeling of IRS, illustrated IRS experimentation, compared relay versus mirror. These are some future work. If you want to pursue further, you can use codebook-based RIS coefficient, channel estimation. Can also use alongside relay also. Relay plus IRS, what will be the performance? IRS is more useful when 100 gigahertz. So when we have a like millimeter wave, so in millimeter wave, loss is very, very large. Okay, so you can put IRS to cover for the losses. Okay, so in above gigahertz is really helpful. Okay. Huh? IRS. They have active IRS, but only passive IRS are only commercially available. Active IRS are not available. Active IRS, if you want to do, you have to implement yourself. Otherwise, it is not available. These results, they have used the active IRS. Okay. Should we go or it's okay? So, okay, so that's it for today. Okay. This is a very different stuff. Next slides. Okay, thank you everyone for listening. Yes, it is also suitable for indoor, but it should be like a very large area. People are also working in the VLC also with mirrors and the IRS both also. So VLC is mostly for indoor. So people are working in that direction also. MATLAB code. So you can look for the ML Johnson website. They have MATLAB code also. Okay. Oh, no, I don't have it. They have it. They have it on the GitHub. You can go and they have it. I have seen that.
Where is it available, sir?
GitHub. GitHub.
Spell it out, sir.
GITHUB.
Others GitHub, sir. There's others.
Yeah. These are all ML Johnson results. So they have the codes there. PPT. Okay, I'll forward.